Hi, welcome back to AP Physics 1, Unit 4, the work energy power unit. So in this video, we're going to look at that first concept known as work. Okay, so work is defined as when you apply a force on an object and causing that object to move. Okay, so so if you look at our gentleman here with the briefcase, right, and so we've got this force, he's applying a force on the object. Notice it is a vertical force, but when you look at the next picture, it shows us that he's actually doing no work on the object. And so that's because the force that he's applying is not in the direction of the force. So that force has to be parallel to the motion. Okay. Now, for work really to be done, you have to look at it in three ways, right? So you have to have three conditions met. The first one, there has to be a force applied. Okay, no force equals no work, right? And why? Because that means there's no change in motion of the object. The second thing, there has to be motion, right? No motion equals no work. Oh, I'm going to spell the word work, put now. So if an object doesn't move or does not move in the direction of the force, there's no work being done. And now here's the last condition. There has to be cause. And so what we say is the force applied has to cause the motion. And so that's this scenario with the gentleman with the briefcase, right? If he's applying a force, yes, but the force that he's applying does not cause the change in motion of the briefcase. Okay, so sometimes what they like to do is they like to ask you those questions. Hey, is there work being done? Or identify a situation where work is being done. And they give you these different scenarios, and you're asking yourself, is there a force applied? Is there a change in motion? And then does that force cause the change in motion? Okay. Now, to calculate work, you can see the equation up there with the up here with the lawnmower. So work equals force times distance times cosine theta. So this cosine theta only appears because, remember, we want parallel forces, right? Or parallel directions, okay? And I put fours, as in 4 for golf. So we want parallel forces, okay? And that's why we have to include that cosine. Now, each force that you apply to an object has the ability to do work. And so sometimes you're asked is to find the net work, okay? And so because work is dependent on that cosine, so if you think about the relationships, work is directly proportional to the force. So more work or more force equals more work. It's also dependent on the displacement or the distance traveled. So the more you apply the force, the more work there's done. But it's also dependent on the cosine and the angle, right? Or the angle. So, and we're really looking at where does it lie between cosine of 0 and cosine of 90. Okay? And because cosine of 0 is 1, cosine of 90 is 0. Now, if your theta equals 0 degrees, right? Or excuse me, I got that. It should be 90 is what I want to write there. Right? So that means your work equals 0. If your angle is between 0 and 90, your work is positive. And if your work is between 90 and 180, your work is negative. And the big force that does negative work is friction. Okay, so let's look at a couple examples. So here we have a pumpkin. We're lifting it up, a 0.8180 meters to check it out. How much work do we do on the pumpkin? So we start with the equation. Work equals F delta x cosine theta. Well, the good thing is we don't have to worry about the cosine part because we're lifting it straight up, so our force is applied in the same direction as our motion, so we can just drop it down to F delta x. Now that F can take on a lot of looks. In this case, the F that we have to apply to the object is the weight of the pumpkin. So what I'm going to do is I'm going to substitute in the weight, right, to mg delta x, because that is at minimum to lift the pumpkin, right, to get it to move at a constant velocity. We have to apply at minimum the weight of the object. And so now I can plug in my numbers. I have 3.2, right, times, sorry, I got to grab my notes because I didn't bring my calculator with me. So times 9.8, or you can use 10, depending on where this question lies. And we're going to move it 0.80 meters. So the work done is going to be 25 joules. Okay, and this is the SI unit for work. It's joules, named after James Prescott Joule. And the reason why we use joules is because later we're going to talk about how work is a transfer of energy. So work and energy are essentially the same thing. And so that they have to have the same unit. Sometimes you will see this unit as a Newton times meter because you're applying a force over a distance, but we just simply call it joules. Okay, here in the next example, we're kind of putting it all together, right? So we have a drum set. We're going to push with 24 newtons. It's going to experience some friction, and then we're going to slide it for 1.5 meters, and the weight of the drum tells us is 54 newtons. Okay, so the way I like to do this is start with the free body diagram, because the free body diagram helps you find what forces are actually doing work on the object, right? So if we're sliding this, drum set to the right, okay, then that means the only forces that are doing work are going to be friction and the applied force. So the normal force and the weight aren't going to do any work, but they do have a factor here because normal force is in the friction formula, right? So mu Fn, which most of the time Fn is mg in this case. So what I can do is find the net force. So the net work is equal to the net force times delta x. And we don't have to worry about the angle because, again, we're pushing in that same direction. And so that's going to be 24, or let's do it variable first. So 24. So it's going to be our applied force minus our friction times our delta x. Well, it's our applied force minus friction, which is mu mg, right, delta x. And now I can plug in some numbers. So I got 24 minus 0.41 times 54. Don't multiply this by 10 because they already told us the weight. If it was kilograms, then you multiply by 10. And we're going to move it 1.5 meters. And what you find is that the friction is 22, or roughly 22. It's a little bit greater than 22. And so the work done is going to be 3 joules, right? So the net work on this drum set is going to be 3 joules. Okay, so in the next video, we're going to talk about kinetic energy, and then we're going to start talking about how does this all kind of fit together in something called the work energy theorem.